Well, good morning. This is Wednesday morning, 9:33, 28th of September, 2016. And it's supposed to be Math 126, Calculus 2. However, I'm the only one in the room, which is not a good sign. Okay, hopefully some of the others of you will be coming in soon, hopefully all of you. But right now I'm the only one here, so let's go and get started. Where we began last time was looking at the method of cylindrical shells. This is 6.4 on page 359. Okay, we had introduced the concept of it, what was a shell, how you got the volume of a shell. Now we're going to look at an arbitrary shape and see how that relates to a shell. Well, here's the arbitrary shape. Some function y is equal to f of x. Okay? Some type of a curve. Now, what's required right now is that this always be greater than or equal to 0. In other words, positive. You don't want this curve crossing the x-axis. All right, we got somebody here. Good to see. I hate talking to myself. So let me... Our Q is here, the Silva. And if you'll flip those lights, turn the left one off, the right one on, yeah, off, and the other one on. Yeah. Good deal, yeah. Excuse me just a minute. Sorry, I've had this. And as I was saying before, where we left off last time was we had talked about the volume of a cylindrical shell, and then we're applying that, and I thought I turned this on. Oh, this one, you have to hold it down. You don't just press the button, you have to hold it down until it beeps. Sorry about that. In my third class yesterday, I was teaching, and then the projector got really dim, and we didn't know why. And anyway, I kept on teaching, and after a while, the bulb blew. And so they didn't take the time to replace the bulb. They just gave me a different projector, which nice and lightweight, small, that kind of stuff. But on the other hand, this also doesn't project as large. And to get it to do as large, I would have to basically back halfway into the room, I think, because the magnifier on the front, this thing I've got maxed out, and get it to maximize. Okay, so that's the best I can do for now, and I've shifted it over. I'll get it back. So here's what we got. We got a function here, y is equal to f of x, and so far the only restriction here, it has to be greater than or equal to 0. We don't want to get below the x-axis here and try to do a shell like that. Okay. So, what we're doing with the shell method, we're doing the volume under this curve, and we like to have dx's, don't have to, but if we wanted a dx here, that's not going to give you a disk. A dy would give you a disk, but then you have to change the y is equal to f of x is equal to g of y. And sometimes that's not an easy function to get, okay? So when we have those that are hard to do this way, then we split our interval from a to b, that's where we're integrating from, rotating this around the y-axis, and pick some increment in the middle, a dx, delta x here, xi minus 1, and you revolve that around the y-axis, and then you get something that looks a lot like a shell. It's the ith shell out here. The first shell was between x equal a to x x equal a to x equal x sub 1, and then the next one, this is the ith shell, x of I minus 1 to x of I, and that is revolved around here. The height is the approximate f of x. It's not exact because that's a curve, but as long as this delta x is small enough, it's pretty close to being a Riemann sum, basically, it'll turn out to be. Okay, so what we have is the area of this would be the height times the width. This is f of x times dx, and then times the circumference that the area cuts as you go around the y-axis. And that would be 2 pi times x, because that is the radius around the y-axis. So 2 pi x times f of x times delta x. That's going to be your approximation on the shell method. Okay? And this shows the ice shell out of many shells, thin shells around here. This is the innermost, x equal a, here's x equal b out here. It's the first shell, second shell, the ice shell, the next to the last shell. Okay, that's the ice shell. And again, the area of that shell is the width of the shell, delta x, or later to be a dx, height of the shell, f of x, to some value within that x of I, and then the circumference that's cut by that is 2 pi x in this case. Okay, there's your thin shell. Now, obviously, here we split that into 1, 2, 3, 4, 5 increments. Okay. Here's your y is equal to f of x. These shells don't quite add up to the full volume. These are basically layers of things that don't quite add up to a full volume. If you double that and make it 10, let me blow this up so it makes it a little easier to see. Okay. Counted before. 1, 2, 3, 4, 5. So that's a fair approximation, but not a good approximation. Okay? But if you double the number of increments and now did 10, it comes a lot closer to being the true volume under that curve. It's still not quite there, but then as you double that again, I'm not sure that's a double. Maybe that's 15 or 16 or something like that. I haven't counted them. But you get even closer to that curve. Well, guess what? As your number of increments increases to infinity, you get closer and closer and closer to that curve. And sure enough, that's what Riemann sums do. Okay? They get closer to the true volume under that curve. Okay? They give those examples, the statements in the book. Let's see if unfortunately they jumped to figure 4 before they've done the equation, which is equation 2. So I'm going to jump over to, here's equation 2. The volume of revolution, I didn't want to do that, the shell method, okay? And I think I've already talked my way through most of it, but let's formally get it here, okay? Now, is this size good enough for you, or would you rather I scoot the desk back? You can see it okay? Okay. The solid obtained by rotating the region under y is equal to f of x over an interval from a to b about the y-axis, and you're using a dx then, so now the dx is forming shells, not disk, okay? Shells, not disk. So you have the volume is 2 pi the radius, that's the circumference, okay? times the height of the shell, that's usually the alpha of x, and the thickness of the shell is your dx. Okay? Integrating from A to B. Okay? Now, the way we've done it, if it's from the y-axis, then the circumference of that is y. I mean, not y, x. Okay? How far you are from the y-axis is your x. So the radius is x, alpha of x is the height of the shell, as long as that's positive, and dx is the thickness of the shell. So there is the volume of your revolution using the shell method. Okay? Remember the disk method, we were summing the areas. Shell method, you're summing the volumes of a shell. Okay? So let's go back to, this is figure 4, which is on the next page, example 1. Okay, I'll blow this up just temporarily so we can get a good look at it before we start on it. All right, the problem is find the volume V of the solid obtained by rotating the region under the graph of f of x equal 1 minus 2x minus 3x squared, plus 3x squared minus 2x cubed over 0 to 1, but you're revolving that around the y-axis. Okay? So you're going 0 to 1, so this is going to have a hollow thing in it. The a is here. Here is the function. F of x is 1 minus 2x plus 3x squared minus 2x cubed. Okay, now that's not the whole function, but you're doing it from 0 to 1. Now they indicate here, and really easy, x equals 0, sure enough, that would be 1, so you show that's graphed properly. They show x equal 1 hitting the x-axis there. Let's see if that works. If you have x equal 1 here, you add your coefficients. 1 minus 2 would be a minus 1, plus 3 would be a plus 2, minus 2 would be 0. Sure enough, that does. So you can't have it any further rotating around the y-axis. You got this. Now, I kind of like this shape because it reminds me of a Hershey's Kiss. And I like Hershey's Kisses. So anyway, this is our Hershey's Kiss example. Okay. So how are we going to do this? We had the formula. How do we do it? Let's see. Yeah. No, I've got to get my pen activated. Okay, here we go. So what would be the volume in that shape? And they've indicated here, they drew a representative very thin disk here. Okay, and that thin disk here, a shell here, I should say, it's x units away from the x-axis, y-axis. X is going from 0 to 1. The thickness here is your dx. The circumference of that is 2 pi x, and your height is your f of x. So that's what we're integrating. Integrate from 0 to 1, x, that's your radius, times your f of x, 1 minus 2x plus 3x squared minus 2x cubed, times the thickness, dx. What would you do first? Yeah, multiply. Distribute that x across there. So it's 0 to 1, and that would be x minus 2x squared, 3x cubed, minus 2x to the fourth, dx. Okay? Now we need to integrate that. What would that be? Oh, wait, I forgot my 2 pi out here. Don't forget that. That's part of the circumference, okay? So the 2 pi is out here. And what you got? X squared over 2 minus 2x cubed over 3 3x fourth over 4 minus 2x to the fifth over 5. Evaluate that from 0 to 1. I'll do the 0 part. Okay, done. Okay. You do the 1 part. And that's not bad either, except that it's a fraction. Okay, but we love our fractions. Okay, and that would be a 1/2, because 1 is real easy, minus 2/3 plus 3/4 minus 2/5. Okay, and the 0 part adds nothing. It's minus zeros. Okay, so it's just figuring out what our least common denominator is. What would it appear to be? You got to have a 5 in it. You got to have a 3 in it. You have to have 2 2's in it. So that would be 15 times 4 is 60, I believe it is, isn't it? So that's going to be 2 pi, and that's going to cancel out a little bit. 60ths, 1/2 is 30 60ths, minus, now 2/3 would be 40 60ths, plus 3/4 would be 45 60ths, right? Minus 2/5, which would be 48 60ths? No. 5 will go into 60, 12 times 12, yeah, 24 60ths. 24 60ths. Okay, I did that twice. Okay. Now, you can add or subtract these any way you want to. I'm really lazy. I do these two together, and that gives me 5 60ths. And I do these two together, and that gives me 6 60ths. And that would be 11 60ths. But the 60 will go into, 2 will go into 60, 30. So I get 11 pi 30ths. Now, I just probably went way too fast there. Are y'all okay with that? Okay, let's see what they got. I forgot it. Ah, there it is, 11 30ths pi. Okay, you can write it any way you want to. All right. That's the volume of a Hershey's Kiss. Isn't that good to know? Okay.
So do you remember all this formula? Do you have to remember all this formula?
Okay, do I?
Yeah.
No, I think through how do I come up with these? Well, if I'm doing a shell, it's the radius, which in this case was x. The circumference would then be 2 pi x. The height is f of x, and the thickness is dx. So I try not to memorize anything. After a while, like, people call me my name so much, I guess I have it memorized. So, but I'm not a good memorizer. I get things crossed up. So I try to remember the concept and put it together from there. That's my way of doing it. Not saying it's good, it just is how I do it. Okay. All right, so that is example 1. Now the next slide is the one we've already covered. That was the volume of revolution on the previous page. Why they got the slides out of order, I don't know. Next we're going to talk about, this is your conceptual insight here. It looks like that same curve we were messing with. Well, I keep doing this. Yeah, I can do this either way. But this is a good review this way. Okay? Now, when you're revolving something or rotating something around the y-axis, if you're wanting to do the disk method, you have to do your dy's, because those would be disks there. Okay? If you're doing the shell method, you do your dx's. You're all around here. Now, to do the disk method, if you're doing dy's, you have to change your y is equal to f of x to some x equal g of y. Now, picture that last one that we had. That had up to x to the thirds, and it had all those other terms. I would challenge you to get that as a function of y. I'll write it down. Of course, as soon as I do, it's going to thing. But let's go on and read this here. Okay. This segment would be the disk method of radius capital R, which is g of y, and then you would do pi r squared. That would be the area there where your r would be your x here. I'm sorry. The radius is some function of y. Because you're doing dy's, then you have to find that radius is a function of y, not x. Okay, y. So that last, and then if you're doing the shell method, though, your height of your radius now is your x. You're doing a dx, and your height would be an f of x. Well, your problem gave you that as an f of x. So that's a straightforward way to do it. To do the disk method, you have to have a dy. So you have to have this radius here in terms of y, not in terms of x. So you solve x as a function of y. That would give you your g of y. And so we'll do that in a minute. So rotation about the y-axis, shell method uses y is equal to f of x as a height, but the disk method requires the inverse function x equals g of y. So what I'm going to do here is, I already had this, I don't know why I went there. If you remember what that function was, y is equal to, or f of x is equal to, which is your y, 1 minus 2x plus 3x squared minus 2y cubed. I'm sorry, x cubed. Okay? Now, what you need is x is some function. Oh, let's not call it f. Let's call it g or something. I think that's what they called it. G of y. And I challenge you to get this function as a function of y. X as a function of y. I can't do that. This is too complicated of a function to solve it for x. You know, you get some function of y. It's just no way. That would be almost, I would say, literally impossible to do. I don't know of any way to get, here's y is equal to f of x. That's straightforward. To convert that, now, if this was a linear function, piece of cake. If it was a quadratic function, yeah, you can do that, take a square root. But if this is a cubic function, that's not a perfect cube on the right-hand side, so I don't know of any way of completing a cube. Maybe there is a way. I don't know of any way to do that. So this would be almost impossible to do it by the disk method. That's why we use shell method. Because shell method, you do your dx, your radius is x, your height is f of x, 2 pi radius, yeah. It's easy to do. It would look like it would be easier to do this method, dy's, but then you have to have the radius here, x is a function of y, g of y. And I can't do it. I mean, I cannot convert that to a function. Some simple functions you can, that one I cannot. Okay. So, next concept here. They jump right to the formula here. When we rotate the region between the graphs of two functions, f and g, satisfying as long as f is always greater than or equal to g, then the vertical segment at a location x generates a cylindrical shell of radius x, and the height is the difference between f and g. Now, all that was blah, blah, blah. Here's the picture, okay? Okay. This time, again, we're rotating around the y-axis, okay? And if we were trying to do disks, what we would have to have are disks this way, and again, you'd have to get x as a function of y, because you're doing dy's, and they haven't given you the functions yet, but it doesn't look like that would be particularly easy. But you have one set of disks here that go from y equal something here to there. Here you have another set of disks, whatever your last value is there. And then the next one is the disk down here that's based on g. Well, that gives you 3 different integrals to make. That's too much work for me. I'm lazy, okay? And I have told you all this, right? I think to be a good mathematician, got to be a little lazy. You always want the simple way. So let's not go with this. Let's go with shells. If you do your dx's, this is going to make a shell that you're going to revolve around the y-axis. The thickness of the shell is your dx. The length of the shell is f minus g. Now, in this case, this f and g can be anywhere you want them to. They could be down here below, so both of them are negative. Or one could be negative and the other is positive, okay? The only requirement is f has to be greater than g, greater than or equal to g, so this is always a positive length here. So you're out of the boat that you have to have f always positive. F could be negative here. You know, it doesn't matter as long as g is always less than or equal to f, okay? So you do your dx. Once you chose that, then you do the height is the difference, f of x minus g of x, so you have f always greater than or equal to g. And then your 2 pi x, that gives you your circumference, times your f of x and your dx, that gives you the integral, okay? And that's what they're showing here. This x here, that delta x that you do here, that rotates around from plus x, rotates around here. The radius is x, so it's 2 pi x times f of x minus g of x, that's the height, times your delta x. That's your thickness. Okay? So that's how we will do this one. Now, is this just a picture? Yeah, that was just an illustration. They didn't give you the functions or anything. Example 2 actually gives you some functions. And they don't do it all here. They just do enough to tease you a little bit. Okay? Find the volume V obtained by rotating the region enclosed by the graphs of f of x, which is x times 5 minus x. That's the upper one here. Okay? And g of x, which is 8 minus x times 5 minus x. Strange way to write these functions about the y-axis. So this is going around the y-axis. Okay. Now, I don't want to do disk, okay? If you did a disk, you would have to have a delta y, and your delta y's would have to be from this function side to that side. Up here, different functions down here. You got, and by the way, you got to figure out where your intersections are anyway. So let's do that first before I get into that. What's our intersection? Well, the intersection is where f is equal to g, right? So let's set those equal to each other. And of course, as soon as I go to write, it's going to shrink. Okay. I think I've got my pen. I do. So x times 5 minus x is equal to g, which is 8 minus x times 5 minus x. Okay? Now, I'm sure well, I'm sure there's a reason they wrote it this way. I just can't think of what it might be. So let's go on and clean this up a little bit. Make this 5x minus x squared equal 8 minus 5x plus x squared, right? Okay? And what we're going to do is set those equals. So let's move the left side to the right side, okay? By adding x squared to both sides, okay? Subtracting 5x from both sides, okay? And that gives us 2x squared minus 10x plus 8 is equal to 0. What do we do with that? What do you factor? Y'all got to be lazy now, remember? Unfoiling or quadratic formula? You could. But when you look at that, what pops out at you?
Oh, we can divide by 2.
Divide everything by 2. That'll make that a 1. That'll make that a 5. Make this a 4. And divide 0 by 2 and you get 0. So let's look at it again as x squared minus 5x plus 4 equals 0. Still want to use quadratic formula? This is such a pain in the neck. Okay. I think I can unfoil this one. Only possible factorization for x squared is x times x. Now look at the sign of my last term, plus, that means these two signs have to be the same, right? And since that one's minus, these both have to be minuses. And what are two numbers that multiply to be 4 or add to be 5? 4 and 1, or 1 and 4. It doesn't matter which way you say it. And this would give you x equal 1 and x equal 4. I wrote them in a different order. So yeah, this is our limits of integration from 1 to 4. Okay? Sure, that's going to get the whole area that's inside there. Okay? That's not even starting the problem. That's just finding the limits of integration. They gave them to us, but I didn't know if I wanted to trust them or not. We've shown that it's true. Guess what? On the test, they're not going to have the pictures necessarily for you. You got to figure this out. So that's why I wanted to show you how to do that. Okay. I think you did that. All right. Now, what are we going to do then? Revolving this around the x-axis, the y-axis, but we're only integrating from 1 to 4, so you don't have to worry about a washer or anything, even though if you did this, that would make a washer, but you don't have to worry about that, because you're just integrating this line all the way around, integrating from here to there, all the lines that do that, okay? And what is that integral? Well, whichever way you want to start it, the 2 pi x, because x is going from 1 to 4, that's always going to be the x somewhere in there. So 2 pi x, so your integral 2 pi x, and then that's your radius, okay? The length of this is what? And they drew the picture for you, so we didn't have to. But that, sure enough, remember, the F was this one up here. That is the one with the minus leading coefficient. This is the one with the positive leading coefficient, so that's concave upward. So we got these in the right order. So it's the difference in F minus G. And frankly, if you look at it, we did G minus F, and we subtracted this from both sides. So F minus G is going to be just exactly the opposite of what we got here. Okay, but we do want this. We don't want to divide out the two. We want this form right here, but it's the opposite of that one. Okay, so that is minus 2x squared plus 5x minus 8 dx. My pen is really slow. I don't know why. Okay. And what do we do first? Oh, and this limit is going from 1 to 4. So the integral from 1 to 4 is multiplied through by x. That would be a minus 2x cubed plus 5x squared minus 8x dx. All right. Let's do the integral. 2 pi times.
I think it's going to be 10x, right? Not 5x.
Second.
You have to put the...
Oh, it was 10x. Yeah, I wrote the wrong number down, didn't I? This is a 10. I got the other two corrected, but I didn't get that one. Okay. Thank you. Save me some grief later. 10x, 10x. Okay. Antiderivative of this would be? Second? Yeah, minus x fourth over 2. You had a coefficient of 2 out there, but you had a denominator of a 4, and 2 will go to the 4. Yeah, okay. That gives you that part. Next, plus, nothing will help you here, 10x cubed over 3 minus 4x squared. Evaluated from 1 to 4. Nothing's going to help you here either because you're going to have to do it all. So let's just get the 2 pi out front. Okay, it's already there. And let's plug in the 4. Minus, and what's 4 to the 4th power? Second? Okay, say that again then. Yeah. Right. Yeah. Okay, so you got the whole thing worked out. Is that what you're saying? With 4 or minus the 1? Just the 4. So what did you get there? 64. Okay. We'll take his calculator's word for it because we trust calculators, don't we? Oh, yes. Okay, where is my eraser? There it is. All right. You said this whole thing was 64. Over 3? Okay. Minus, and when you put a 1 in for that, that's going to be a minus 1/2, a plus 10/3. Have you already done this one too? Minus 4. Second? Negative 7 over 6. Okay. So you got a 2 pi times a 64 thirds minus a minus. Is that what you're saying? Which is a plus 7/6. Is that what you said? 7/6. Okay, we're taking, again, his calculator's word for it. So we're going to need to double these. So this will be 128 over 6. Okay. And then the 2 will go in the 6 and make this thirds down here. So this is going to be 135 pi over 3. Whoa. That actually, if I did it right, that actually reduces. 3 will go into 13 4 times. 3 will go into 15 5 times. 45 pi. Is that what they got? Look at them, they got it right. Okay. Were you using a calculator or reading out the book? Okay, good man. Okay. They got it out of the book. Okay. So, that's what you wind up with, 45 pi. Seems like a pretty hefty sized volume, but you're revolving that around. By the way, that makes a donut, don't you think? I like to think about it as a donut. You know. If you're healthier, you may think of it as a bagel, but I prefer donuts. Okay. That's actually sort of called a torus, is mathematically what you would call that. Okay. They didn't really show the picture of that. 45 pi. Now, continuing, rotating around the vertical axis. I'm guessing when they say a vertical axis, this is not necessarily the y-axis, some other one. So this looks like example 3. I think, yeah, this is it. Use the shell method. They don't have to tell us that. I think we would have done it ourselves. To calculate the volume V obtained by rotating the region under the graph of f of x is equal to x to the 1/2. I'll blow this up temporarily. I feel like a terrorist by blowing things up, but let's not do that. Okay. All right. F of x equal x to the minus 1/2. Okay. Well, there's the graph of that. When x is equal to 1, y is equal to 1, so obviously the scale of y is not the same as the scale of x. And then out to x equal 4, that would be 1/2. So, yeah, that would be, looks about right there. So there's your curve. Did they say between those two limits? Or yeah, over the interval from 1 to 4. About the axis, x equal -3. Over here, we're not doing about the y-axis anymore. Well, you could do this problem either disk or shell method. Well, it won't be disk method, the washer method. Okay? Because this is a real easy thing to get x in terms of y. Square both sides. Well, let's see. What I think I would do is multiply both sides by x to the 1/2. And that becomes a 1, so it's y times x to the 1/2. Let's see, how would I do that? I think the easiest thing would be to square both sides. And that gives you 1 over x is equal to y squared. So x is equal to 1 over y squared. So you could do it that way. I think that would be, and then do your disk method. But notice your disk method, you're going to have delta y's here, but then out here you're going to have just a disk that's a radius 7. So you got 2 integrations to do, but the bottom is really easy. You can do that without actually doing any integration. But then you have the differences and all that kind of stuff. So I think that with the washer method, you could do it, but it wouldn't be necessarily any easier. Let's look at the shell method. The shell method, you're going to choose a delta x here. I like to draw that as a delta x, not that. The x is somewhere between 1 and 4, but your radius is not x, it's x plus 3. X minus a minus 3, which is x plus 3. That's your radius as you're going from 1 to 4. So that's the difference here from what we had before. So now your radius is x plus 3. Your height is x to the 1/2, negative 1/2, and your delta x thickness is that. So it's 2 pi r, where r is x plus 3. So, goodness gracious, this head cold is driving me nuts. I don't know if it's cold, it may be allergies. Whatever it is, it's driving me nuts. Okay. So what would be your integral? 1 to 4. And you're using that on x, so this is going to be a dx, which is also the thickness of the shell. 2 pi on the outside. That's from the circumference. Your radius is now not x anymore. You're not revolving around the y-axis. You're revolving around that. Yeah, so that would be x plus 3. And then your height is your y function, which is x to the minus 1/2. Okay. Now, it might look more complicated, but it really isn't a bad thing. Again, multiply through, multiply that monomial times the binomial, and you get 2 pi, the integral from 1 to 4, and that would be x to the minus 1/2, no, x to the positive 1/2. I was doing the second one first. Okay, get my pen back. Goodness gracious, his head. X, which is x to the 2/2 times x to the minus 1/2, is x to the positive 1/2 plus 3x to the minus 1/2. Okay, then your dx. Okay. Okay. Yeah, I'm multiplying this times this. The exponent here is 1, or to make it easier, make it 2/2, right? Multiply x to the 2/2 and x to the minus 1/2. Keep the base, add the exponents. 2/2 minus 1/2 is 1/2. Yeah. Okay? And then the second part is plus 3 times x to the minus 1/2. Okay? Now, these are power functions, fractional powers, but they're still just power functions. So I think we can do that integral pretty reasonably. The 2 pi is out front. And what would be the antiderivative of x to the 1/2? X to the 3/2, right? And then you divide by 3/2, which is the same as multiplying by 2/3, right? Okay? Plus, not going to, yeah, it'll say a plus. The 3 is going to be here, but that now is x to the 1/2. No, you add 1 to it. And then you divide by 1/2, which is multiplying by 2, so it's 2 times 3, okay? And you'll evaluate that from 1 to 4, okay? So let's go down here maybe and do that. 2 pi times, when you put a 4 in there, you got 2 times, I like to take the square root first if I can, so this, the over 2 here, be the square root of 4 is 2. 2 raised to the 3rd power is 8. So it'd be 8/3 plus, and that's a 6, and square root of 4 is 2, okay? Minus, put the same thing in but with 1, well, that's going to be 2/3 minus 6, right? So put a 1 in for x to any power, it's going to be 1. All right. That's 2 pi times, this is 16/3 plus 12 minus 2/3 minus 6. Okay, I'm going to sort of cheat a little bit and do 2 pi times 16/3 minus 2/3 is 14/3 minus 6. Well, I need that in terms of thirds. Let's make that 18/3. Why do I wind up a negative number here? Oh, that's a plus 6. Goodness gracious. What were you thinking when you wrote that, huh? Yeah. So that would be 32 thirds, right? And twice that would be 64 thirds pi. Is that what you get? Oh, and that's what they got too. Good for them. Okay, good deal. So when you see something coming out wacko, think, wait, that can't be. You can't have a negative volume. Oh, I'll put a minus on that little plus. Okay. So you can help sort of zoom in on what your error was. All right, does that make sense? I'm sorry, I can't breathe. That was example 3. All right. I think example 4, I believe, is this next figure. I hope it is anyway. Rotating around the x-axis. Okay? Use the shell method to compute the volume V obtained by rotating the region under y is equal to 9 minus x squared. That's, let me blow this up a little bit. Okay. Sorry, I'm having trouble breathing. All right. By rotating the region under the y is equal to 9 minus x squared, that's that curve there. Now let's just make sure that everything is here. When x is 0, this y is 9. When x is 3, y is 0. Yeah. Now, obviously, their scale is wacko here. This is 3 here, and that's 9 there. So they've compressed the y scale and expanded the x scale. So if I were drawing this, it would look like that, you know. So that's the I have trouble breathing. That is the curve. We're revolving this around the x-axis. Okay. Now there's a big part of me that says, why aren't you doing a disk? The disk would be dx, and the radius of this would be your y. That would be 9 minus x squared. And its pi r squared would be the area of that disk. Thickness is dx. Integrate that from 0 to 3. Now, I can't remember for sure, but I think we did that. Okay, we did that back in the last section. That's the easiest way to do this problem. Okay, but they're saying use the shell method. When the shell method, since you're rotating this way, you're going to have to do a dy. But if you do a dy, you've got to change this to a function of x. X as a function of y. So what we're going to do is add x squared to both sides, and then subtract the y from both sides, and that will give you x squared is equal to 9 minus y, right? Then take a square root, because we're only doing the positive square root, so you only need the 1, and that would be square root of 9 minus y. So that's what we've got here. So that's going to be your x, so that's the radius, not the radius, that's the height of this disk, of the shell, okay? The thickness is your dy, and your circumference is 2 pi y, because that's your radius here, the y. When you're rotate that around the x-axis, which is indicated here. And this cold air blowing on my back is doing nothing for my head. Okay, so there is your formula. So let's, of course, this is blown up, so as soon as I go to write, it's going to shrink down again. And this would be the shell method, 2 pi times the integral. Okay, now you're doing your dy's, and your y's are going from 0 to 9. Okay? Your y is your radius, so you've got the y in there. And then you've got your f of y, that's the height of that, which is your x length. That's the square root of 9 minus y. And your thickness is then a dy. So there's your formula. I don't like this nearly as much as this method of this. I mean, nowhere close. Okay. One big problem you've got is how in the world are you going to evaluate that? What would be your suggestion?
The square root as like 9, 102.
Second.
Can we write the take the square root of and can we write like 9 1/2 like and y minus y 1/2?
Okay, I see. 9 minus y to the 1/2 power.
Yes.
Okay. Yeah, I see what you say. Okay. Okay. Let's do it. 2 pi times the integral from 0 to 9 still of y times 9 minus y to the 1/2 power dy. That's exactly the same thing. And that's usually the best way to go. I don't like to integrate radicals. So, yeah, I agree with you there. But we still got problems, don't we, Houston?
We can distribute multiply by y.
Not because that's a radical there. If you're multiplying by y, you have to multiply by the square root of y squared. Then you could do that.
Why we can't take the
Because,
without putting the brackets
no,
outside?
yeah, but you see, if this was your binomial and this was to the 1/2 power like we had last time, yeah, you can do that. But with the thing, this is the radical, you have to get this into the same radical before you can do that. So you could do that. But let's see, maybe,
I would take that 1/2.
right?
Like it's like 9 to the 1/2 minus.
No, it isn't.
We can take
No. Okay, yeah. Radicals aren't, those are not linear functions. So you can't do that. Yeah. Sorry, good try. Okay. Here's what we do. Take the innermost part of the most complicated part of the function and substitute. Okay? I would say that. Okay? So what would that be? Let (9 minus y) equal, or maybe I should have said it the other way. Let u equal 9 minus y. Y'all are more used to that, aren't you? Okay. Let u equal, we always use u, I don't know why. I like to use u, I don't know. Okay. 9 minus y. Okay. Then, what do we do next? Du is equal to? Minus dy, isn't it? Okay, but we don't have a minus dy, we have a plus dy, so let's move the minus over here with the minus du. Okay? So we're going to change our variable from y to u. If we're going to do that, we also need to change our limits. Okay? And when when y is equal to 0, u would be, y is equal to 0, u would be 9. And when y is equal to 9, u would be 0. Okay? But remember, we had a minus du, so you have to have a minus sign. Well, guess what? I don't like to do the big number on the bottom. I want to flip those, but when you do that, you negate, right? So that then loses this, so you go back to being 2 pi integral from 0 to 9, but now we're going to put the du in here, and ooh, we got a y in there. But you see this thing right here, this means solve for y, and you get y is equal to 9 minus u, isn't it? Okay, so this becomes the y becomes a 9 minus u, and then this you have a u to the 1/2, and guess what? Now we can multiply through. So you see what that did for us? All right, now we can do what you want to do the first time, because that is a monomial you can multiply by a binomial. Okay, so that's going to be 2 pi, and our limit stayed the same, 0 to 9, of 9u to the 1/2 minus u to the 3/2 du. Okay? Now I think we can integrate that one. 2 pi times, what would that be? Okay, it'd be u to the 3/2, so then you'd have a 2/3 here, but then you have the 9, not 3 will go into that 3, so that's going to be 6u to the 3/2, okay? Minus u to the 5/2 times 2/5, right? Divided by 5/2, which is multiplied by 2/5. We're going to evaluate that from 0 to 9. Okay? I can do the 0 part. You do the 9 part. Okay. 2 pi times, okay, I like to take the square root first. And this has a 6 here. And the square root of 9 is 3. And 3 cubed is 27. So 6 times 27. Y'all get that? Yay or nay? Got it? Minus. Now this one's not quite as nice. Okay? The square root of 9, again, is 3. 3 to the 5th power, though. 3 to the 4th is 81. And to the 5th would be 243. Ooh, boy. 2 times 243 over 5. Okay. Most things, this is going to be a messy fraction, I think. I'm going to write it up here. 2 pi times, well, 6 times 27, 6 times 25 would be 150. And a second? 162. Okay. Minus, and this would be 486 over 5. Okay. And this would be 2 pi times, let's make that over 5 too. So that would be 10, 31, 810. I believe that's right, isn't it? Okay. 486 over 5. Now I think I can do that subtraction. Let's see, what do we get? That would be 324 over 5. Okay, so I think that would be 648 fifths pi. Strange number. Strange number. 648 fifths pi. Yep. That's what they got. Good for them. Okay. Does that make sense? It's a shame when the hard part is your fractions, you know, the regular math that you did back in, what, 4th grade or something like that, you know. The calculus is much easier than that. Okay. They have a summary here. And I think this summary goes over this. And let's just talk through what they're doing here. Okay. First, they have some function here. You're revolving, or the area here between A and B and this f of x revolving around the y-axis. Only way to do that is the shell method. And you have a dx, and the x will be the radius because you're revolving around the y-axis. So 2 pi x, integral from a to b, 2 pi times integral a to b, 2 pi x, f of x, dx. Yep, that'll work. When you have the difference of two functions, not the function in the x-axis, the difference of two functions, in this case, they can be positive, negative, it doesn't matter as long as f is greater than x. Here, f has to be greater than or equal to 0. Here, f of x has to be greater than or equal to g of x. That's all that's required. Same thing here, revolving around the y-axis. Then you just have your 2 pi, radius is x, so you're going around the y-axis. But the height now is f minus g. Whatever those functions are, as long as f is greater than or equal to g. And then your dx is your other. Okay. The third scenario here would be this single function area over that, so it just has to be greater than or equal to 0, but you're revolving this around some axis x equals c. Okay. Now, this c appears to be between 0 and a, 0, any of this. So now your radius is x minus c, but the rest of it's exactly the same. 2 pi of the radius x minus c times the height f of x times the dx. So yeah, that's the only difference there. If c happened to be negative, it'd be x minus a minus c, which would be x plus c. Okay, so that would be fine. Now, the one that we didn't do is move the c on the other side of the shape, over there. Now your radius is c minus x, right? And it's c minus x, 2 pi times c minus x, integrated, of course, between 0, a and b, that's the same, f of x. So that part we didn't do wasn't in the text, but they put it in the summary. But there you do, the radius is now c minus x. Radius is always long minus short, you know, of whatever your rotation is. Does that make sense? All right. How are we doing on time? 10:45? All right, we've got plenty of time. Okay. Okay, let's move back to, I want some screen that has a lot of white on it. This isn't bad, is it? So let me erase all this. Okay, this is not the picture we're using. We're doing preliminary questions. Consider the region R under the graph of a constant function f of x equal h over an interval 0 to r, little r. Okay. Visualization is a big part of this one. Consider the region R. Oh, okay, got it. Okay. So, forget this. Okay. Here's your graph. Consider the region R under the graph of a constant function f of x equal h. Okay, there's your constant function f of x equal h. Okay, under the graph of the constant function that over the interval from 0 to little r. So this is what we're looking at. That is your region R under the graph, f of x equal h, from 0 to r. Okay? So this is the region that we're interested in. Okay? Give the height and the radius of the cylinder generated when x is rotated about the x-axis. So you're going to rotate this the first time about the x-axis. So what is first? The height, and second, the radius. Okay. Rotating that, and it says using the cylinder method, or they don't say, they say of the cylinder generated. So the cylinder here would have to be a dy. If you're rotating around the x-axis, this would be the slice of a cylinder, right? Going around here, right? So your radius here is the fixed number r. Usually I call that r, so I don't know how to write that. Radius equal r. I can't use capital R either, so a radius. But the radius would be little r, and I said that wrong. The radius would be y, and the height of the cylinder would be little r. So again, I don't know what to call this. The radius would be y. Let me just spell it out. Radius would equal y, and the height of that would equal little r. Okay? That's all they're asking for. When you're revolving that around the x-axis, your radius is your y value, and your height is of that delta r strip, a delta y strip that you have there, that would be r. Because everywhere the height is r. Okay? Let's make sure that we're doing the same thing they are. This is 6,4. The radius is h. Right. And the height r. Yeah. Right. Oh, okay. I'm sorry. They're doing the whole thing. They're not integrating. They're doing the whole thing. The radius would be h then, and the height would be r. Yeah. Okay. So the radius is h. We just did a portion of that. Yeah. They're not integrating, they're just going to do it. So the radius would be, okay. Okay. Yeah, I said h, but this should be height, H-E-I-G-H-T. Okay. The height is r. So there's no delta here. I drew it as if there would be. No, they're saying if you rotate this, what is the radius that you do of the cylinder that you form? That's going to form a cylinder. The radius of the cylinder would be this h, and the height of the cylinder would be this r here. So that's what they meant. They're not doing a delta y. They're not doing any deltas. They're just calculating the volume of the cylinder. Right. No integrals at all. Okay. So let me take this out of there I thought they were doing that. Yeah. Yeah. Okay. I sort of botched that up, didn't I? Okay. Now, what if you're doing around the y-axis, that you're rotating around this way? Now, what is your radius will be r, and your height will be h. Yeah, just like you would expect them to be. The way they named them. The radius was h, the height was r, the radius r, and the height was h. Got it. Duh. Okay. Number 2. Let V be the volume of a solid of revolution about the y-axis. A question. Does the shell method for computing V lead to an integral with respect to x or y? So let's draw this one down here. Okay. Let V be the volume of a solid of revolution about the y-axis. Okay. So let's say here's your function, and you're going around the y-axis. Okay. Does the shell method for computing V lead to an integral with respect to x or with respect to y? The shell method. Second? Oh, okay. You're going around this. A shell would have to be there, right? This would be your dx, so you have to be integrating with respect to x. Do you see that? With respect to x, okay? The B part says that the disk or washer method for computing V lead to an integral with respect to x or y. If you're revolving around the y-axis, a disk or a washer, if you did this, then you would be integrating with respect to y. So that would be y. It better be. Yeah, with respect to y. Good deal. Number 3. Only have 3 on this set. This is, let me erase all that ink. I'll put some of that back. Number 3. If we rotate the region under the curve y is equal to 8 between x equal 2 and x equal 3 about the x-axis, what answer should the shell method give us? Rather strange. So let's draw this. Rotate the region under the curve y is equal to 8. There's a constant function there. Between x equal 2 and x equal 3 about the x-axis. Okay? So here's your y-axis. There's your x-axis. Here's y is equal to 8. We're going to call up here somewhere. This is 8. Y is equal to 8. Okay? Between x equal 2 and x equal 3. So you're doing this area here around the x-axis. We rotate the region under the curve y is equal to 8 between x equal 2 and x equal 3 about the x-axis. What answer should the shell method give us? Well, what do you have if you rotate that around the x-axis?
We have to subtract
Okay, you have to have what now? Okay, if you're rotating this around the x-axis, what are you forming? You're forming a that's what you get, isn't it? Sort of a little wheel, right? And what's the radius of that wheel? Eight. And so the area of that wheel would be okay. And then the thickness of it is 1. 3 minus 1. So it would be pi r squared. Pi times 8 squared is 64. 64 pi times 1. So you better get 64 pi. Your shell method should give you that because your disk method just did. Okay? basically you did a disk method for the whole thing at once. So hopefully that gets you 64 pi. Exactly. Okay. So they did an integral with it, but there was really no reason to, but you could. Okay. Homework exercises. Do any of the odds 1 through 5. Do any of the odds 7 through 11. Do number 13. It says you need a graphing utility. Yeah, probably y is equal to sine of x squared. That might be useful, but you could still probably work it without. But if you don't have one, don't sweat it if you don't want to. Any of the odds 15 to 19. Any of the odds 21 to 25. Do 27. That's sort of an interesting looking problem. And any of the odds 29 to 33. Any of the odds 35 to 39. Any of the odds 41 to 45. And any of the odds 47 to 53. Do either 55 or 57, or both if you choose. And then try to give 59. It's a little more esoteric, but you can probably handle it. And then if you really want to dig for it, you could try 61 if you wanted to. Talking about an ellipsoid, but you don't have to do that if you don't want to. All right, any questions on 6.4? Okay, the last section in chapter 6 is 6.5, and we got what, about 13 minutes, right? Because we go to 11:10? Yeah, okay. So let's get what we can done in 6.5. Last section in the chapter, so when we finish this, I'll give you a test in chapter 6. And basically, right now, I would say it's going to be 2 questions for each section. Okay? And y'all are still working on the first one, right?
Yeah. Is it okay if I bring next Monday?
Oh, that'll be fine. Yeah. Just encourage you to get it in before I give you the next one. And I might give you the next one on Monday, but it may be Wednesday. But don't have them pile up too bad. Okay? So, let's see. Current slide. All right. This almost looks like a picture from a Greek tragedy or something like that, doesn't it? Or Italian, push me, pull you, was that in the Dante's Inferno or something like that? You know, never mind. But we're not talking about that. Work and energy. All physical tasks, from running up a hill, turning on a computer, require an expenditure of energy. When a force is applied to an object, now both of you had physics? Doing physics now, okay. So this is old hat to you, okay. Occasionally I have a calculus class that they're math majors in that don't have to do physics. I suggest that's probably the best science for them to take, but they don't have to. They can do any science. So that's why I asked the question. So y'all are both pre-engineering, right? Okay, good. Okay, but when a force is applied to an object to move it, the energy expended is called work. When a constant force is applied to move an object a distance d, constant force, a distance d, in the direction of the force, then you simply have work is equal to force times distance. Okay? So here are the couple moving the rock, exerting a force on the rock, moving it a distance b from A to B. So the work expended, as long as they're doing a constant force in the same direction of the displacement, then the work is force times displacement. Simple, straightforward formula. Actually pretty cleverly written too if you had imagined this is a force vector here, and this is a displacement vector here, then what kind of multiplication is that? A dot product. And what does a dot product produce? A scalar. Yeah, work, which is a scalar value. Force is a vector, displacement is a vector. The dot product of two vectors gives you a scalar. Work is a scalar quantity, not a vector quantity. Okay? And work and energy is a scalar quantity, not a vector quantity. Okay? So that's not what they were getting at, but the symbology suggested. The SI system unit for force is a Newton, abbreviated, capital N, and is defined as 1 kilogram meter per second. That's what 1 Newton is. Energy and work are both measured in the units of joule in the SI system, and a joule is a Newton meter. 1 Newton force over a 1 meter displacement. Okay, and that's a joule, capital J, because it's named after John Jacob Joule. Okay, Newton, of course, named after Sir Isaac. Man, my eyes are dry. Okay. Now, in the British system, the unit of force is the pound, and energy and work are measured in foot-pounds. But if you're talking about basically heat energy, we often use calories, and sometimes use BTUs, and sometimes, so a foot-pound is approximately 3/4 of a joule, a little less than that, or about a little bit more than 3 calories. Now, there's an interesting little quote from Richard Feynman, who was probably one of the best communicators of physics, to be a brilliant physicist who really knew how to get it down. For those who want some proof that physicists are human, the proof is in the idiocy of all the different units with which they use for measuring energy. Okay, it shows how human they are. Character of physical law. Just a little commentary there, because we already named 4 units of energy right here. Okay. To become familiar with the units, let's calculate the work required to lift a 2 kilogram stone 3 meters above the ground. Okay? Now, if I'm lifting a stone, I don't happen to have a stone in here. Let me use the book instead. So I'm lifting this book. I hate to do that to those ionizing pins. They're expensive. 3 meters up, okay, I'm having to push upward against what? Gravity, the weight, which is the force due to gravity. Okay? The force due to gravity is weight, which is mg. M is the mass, and they told us it was a 2 kilogram stone, which this book was probably closer to 1. 3 meters above the ground, so that would be 2 kilogram times the acceleration due to gravity, 9.8, so that would be 19.6 newtons, 3 meters, 3 times 19.6, it's going to be 57 or so, some odd. 58.8 joules. Okay. Kilogram is a unit of mass. Pound is a unit of force. So if you have kilograms, you have to get that to newtons by multiplying by 9.8. If you have pounds, you're already in a force unit, so you don't have to multiply by anything. Okay. Okay. So work done by lifting a 2-pound stone. Now this is closer to be a 2-pound book. 3 meters into the air would just be 2 times 3 is 6. But the units are foot-pounds. No, was it 3 feet or meters, did I say? 3 feet. I said meters, but it's 3 feet. So lifting that 3 feet, which is about 1 meter, you would do 6 foot-pounds of work. Okay? Work is measured in foot-pounds. Say again? No, because force, pounds is already a force unit. Yeah. What is the mass unit for the British system or the English system, U.S. customary system? You never use it. You know what it is? A slug. Slug, yeah, never use it, okay? That's what I said. But it's never used. It doesn't even have an abbreviation. If you're using it, you have to write out the word S-L-U-G, slug, you know, or slugs with an S on it. So no one ever uses that, okay? So, yeah, when you use pounds, the acceleration due to gravity is already in that. Okay. Now, what is this? Okay, and there was our I just love the way this book has this whole slide and they put it on this little bitty thing. So even blowing it up, it's small, okay, but at least it's readable now. Okay, so work is force times displacement. As long as the force and the displacement are in the same direction, then that's a true statement. If they're not, just make those vectors and put a dot product in, and it's still a true statement, because then you take it into account. Now we got this couple again. They've moved it a little ways, haven't they? Don't know quite why they're moving the rock, but they obviously think it needs to be moved. The work to move an object from, say, one incremental thing to the next. Say you're going from A to B, and you're going to break this down into segments, partition, and you're going to have n partitions in that. The first one being x of 0, which is A, the last one being x of n, which is B. So anywhere in the middle here, you're the I minus first to the I partition. So to move it from there, especially if this is a variable force, okay? The old guy is running out of juice here, and he's pushing less and less hard, and the wife is trying to keep it constant, so their total force is down, decreasing with displacement, okay? Actually with time, but we'll call it displacement. So now this isn't a constant force, it's a variable force. So now we consider for that increment, that's approximately a constant force over that very small thing, even though it's less than it was here, or more than it was there, it's just changing from there, but it's about the same. So then what we've got is you're setting up an integral. Integrate all those forces times these little increments here, and that's the total work that you've got done, okay? And that leads to our formula for work, okay? Definition of work. And again, you've had physics, so this is nothing new to you. I don't know about the other guy, Theo. He's in physics. Work is the work performed in moving an object along the x-axis from A to B by applying a force of magnitude f of x, which implies a variable force. Then that work is the integral from A to B of f of x dx. Okay? So there's the simple way to write that. And it's time. Oh, what sad words those are, aren't they? Okay, get over it. We'll pick up next time with Hooke's Law then. Okay, we didn't get enough covered there to do any example. So after we do Hooke's Law, you can get one of those. Good deal. And I'm going to name this one just 6.4, even though we got a little bit of 6.5 done.